In this video, we're going to be beginning chapter 8, dealing with exponential astonishment. And in section 8a, we're going to talk about growth, both linear versus exponential. Okay? Now, there are two basic growth patterns. One of them is linear growth that occurs when the quantity grows by the same absolute amount in each unit of time. So in this case, it's going to be a numerical value, a constant numerical value that increases or decreases over a period of time, each unit of time. And then exponential growth, that occurs when the quantity grows by the same relative amount. And what that means is by the same percentage in each unit of time. So pretty much when you see a numerical value and it's the same numerical value in each unit of time where it's growing, it's going to be linear growth. Now, if you see a percent and it increases over each unit of time by some percent, that will be exponential growth. Okay, now here's an illustration here. Straight down, which is this blue line that you see here, that's going to grow by the same absolute amount each year. So it's a linear growth. And as you can see, it's just going to be a straight line. And Power Town grows by the same relative amount each year. Here you see that curve. That's in red. In that case here, that would be exponential growth. And usually exponential will be in the graph of that will be in the form of a curve, looking like the one in red. All right, now let's look at a few examples where we're going to have to determine whether we have a exponential growth or linear growth. Okay. Here we go. All right, in example 1, the population of a town is increasing by 635 people per year. State whether this growth is linear or exponential. And if the population is 1,800 today, what will be the population in 5 years? Well, we can see that it's increasing by a absolute numerical value of 635. So in this case, this would be linear growth. Here the population growth will be linear. And what will be that population in 5 years? So here, the population was 1,800. So we're going to add 635 each time. So here we're starting off with 1,800. So after the first year, if we add 635 to that, it will be 2,435 after the first year. And then if we add another 635, this will be 3,070 after the second year. And add another 635, as you can see, we're going to have 3,705 after the third year. And then after the fourth year, if we add another 635, this will be 4,340. And then finally, if we add 635, after the fifth year, we're going to end up with 4,975. So the population in 5 years will be 4,975. Okay, now let's look at this next example, example number 2. The price of a computer component is decreasing at a rate of 11% per year. State whether this decrease is linear or exponential. And if the component costs $40 today, what will it cost in 3 years? Now, in this case, the cost is going to be decreasing at a percentage of 11%. So here it's going to be decreasing by a percent. That means it is exponential. This is an exponential decline here in price. So now, what will the computer component cost in 3 years if it costs $40 today? So here, let's say here after year 1, 11% as a decimal will be 0.11. Here you take 11%, drop the percent sign, divide that by 100, you'll get the decimal form of 0.11. We're going to multiply that by $40. So on your calculator, if you do 0.11 times 40, you're going to get, into 2 decimal places, this will be 4.40. That's the amount of the decrease. So to find out what the cost is after the first year, we take that $40 and subtract $4.40 from it. You'll end up with $35.60. That will be the cost of a computer component after the first year. Now, after the second year, it's still going to be decreasing by 11%, so be 0.11 times this cost of $35.60. Now, if you do 0.11 times $35.60, if you round this off to 2 decimal places, it would be $3.92. That's the amount of the decrease after the second year. And now we're going to subtract $3.92 from the $35.60. You'll end up with, if we subtract that, it'll be $31.68. That will be the cost of a computer component after the second year. And then finally, after the third year, still decreasing by 11%, so we 0.11 times the amount after the second year, $31.68. So multiply 0.11 times $31.68 by, and round to 2 decimal places, this will be $3.48. That's the amount of the decrease after the third year. Now we're going to subtract that $3.48 from the $31.68, and then you'll end up with $28.20. That amount will be the cost of a component in 3 years. So that's how we calculate this. Here, it's a little bit more work on this one than it was with the linear one here because it is exponential. Okay. All right, the next example is to state whether the decay is linear or exponential and answer the associated question. The value of a car is decreasing by 11% per year. If a car is worth $9,000 today, what will it be worth in 2 years? And we want to state whether that decay is linear or exponential. In this case, it's decreasing by a percent, not an absolute number. It's decreasing by a percent. That tells me this will be exponential. Okay? In this case here, that decay is going to be an exponential. And we call it an exponential decay, by the way. And what will the car be worth in 2 years? Well, let's find out what it's worth after the first year. So after year 1, we're told that it's decreasing by 11%. Now, again, 11% as a decimal will be 0.11. We're going to multiply that by the value of the car today, $9,000. I'll go ahead and bring up my calculator. So here, if I do 0.11 times 9,000, the amount of that decrease will be $990. But I have to subtract $990 from the $9,000. So here, if I do 9,000 times 990, you're going to end up with $8,010. So 9,000 minus 990 will give you 8010. So after the first year, the value of the car is going to be $8,010. Now after a second year, it's still decreasing by 11%, so we'll have 0.11 times, now it's going to be 8,010, because that's the value at the end of the first year. So 0.11 times 8,010 will be 881.10, or $881.10. That will be the amount of that decrease. Now we're going to subtract that $881.10 from the $8,010. So 8,010 minus $881.10, you'll end up with $7,128.90. Okay. And yeah, I forgot to answer this part right here. Since the quantity decreases by the same, in this case, it's the same relative amount, because it's a percent. And the value of the car in 2 years will be $7,128.90. Okay. Okay, here's another example. State whether the growth or decay is linear or exponential and answer the associated question. The value of a house is increasing by $2,400 per year. If it is worth $160,000 today, what will it be worth in 5 years? In this case, it's increasing by an absolute amount of $2,400. So here, this will be a linear growth. It's increasing and that means we have a growth, a linear growth. It's increasing by a dollar amount, by an absolute amount. And what will be the value of the house in 5 years? Well, let's say after the first year, it's worth $160,000. Now, if we add $2,400 to that, it will be, after the first year, $162,400. And then after the second year, now we'll take that 162,400 and add 2,400 to that. You'll get $164,800. And then after the third year, 164,800 this time. We add another 2,400 to that. You'll get $167,200. And then the fourth year, here we add 167,200 to another 2,400. That would be $169,600. And then finally, after the fifth year, 169,600. Add that to the, add another 2,400 to that. You'll end up with $172,000. So after 5 years, the house will be worth $172,000. Okay. Okay, now let's talk about the impact of doubling. The impact of doubling. And that's going to be the time it takes for each doubling depends upon the rate of the exponential growth. Okay? So in this case, in example 5, a king in ancient times agreed to reward the investor of chess with 1 grain of wheat on the first of the 64 squares of a chess board. On the second square, the king will place 2 grains of wheat. On the third square, 4 grains of wheat. And on the fourth square, 8 grains of wheat. If the amount of wheat is doubled in this way on each of the remaining squares, how many grains of wheat should be placed on square 20? Also find the total number of grains of wheat on the board at this time and their total weight in pounds. We're going to assume that each grain of wheat weighs 1/7,000 of a pound. 1/7,000 of a pound. All right, let's see how we're going to do this. The way I would do that is create a table. So, let's say we got a square here, and then number of grains. Let's see if we can recognize a pattern that's going on here. So like with square 1, there's only 1 grain of wheat. Square 2, now there's 2 grains of wheat. Then square number 3, it's doubling to 4 grains of wheat. And then 4 will be 8 grains of wheat. Okay, and we can continue this pattern on and on and on until we get to square number 20 to get our answer. But in this case, if we look at this, I can write that. I can look at these number of grains here in that column and look at that as powers of 2. Like the 8. That's 2 to the 3rd power. If you recall, 2 to the 3rd, that's 2 times 2 times 2, which would give us 8. 4 is 2 to the 2nd. The 2 is, of course, 2 to the 1st. The 1 is actually 2 to the 0 power. If you recall, any non-zero number to a power of 0 is always going to be 1. Okay? So I see this type of pattern that's going on here. Okay? Now I'm going to use that to find out what would be the number of grains on square 20. Now, if I look at these exponents here, I can see that these exponents for each one is 1 less than the numbered square, like in this case right here. That exponent of 3 is 1 less than the numbered square of 4. The exponent of 2 here is 1 less than the numbered square of 3. And the exponent of 1 and 2 to the first, that's 1 less than the numbered square of 2. And 0 is 1 less than the numbered square of 1. So here, I can say that the power of 2 is 1 less than this numbered square of 20, which is going to be, in this case, 2 to the 19th power. And on the calculator, I think we can do 2 to the 19th power. So if I do 2 and then press the hat key and then type in the 19 for my exponent, that would be 524,288. So on square 20, there will be 524,288 grains on that square. Okay. Then the next question they ask is how many total grains of wheat should be on the board after the grains of wheat have been placed on square 20. So we're looking at the total number of grains. Okay. So on the first square, there will be a total of 1. Now, after the second square, it's going to be 2 plus the number before it. 2 plus 1 will be 3. And then after square 3, you're going to have 4 plus the numbers before it. 4 plus 2 plus 1. That's 7. And then on square number 4, there will be 8. So the total will be 8 plus 4 plus 2 plus 1, which will be 15. Let's see if I can find a pattern that's going on with this one as well. Okay. I know 15 is 1 less than 16. And 16 is actually in a power of 2, 2 to the 4th. Because 2 times 2 times 2 times 2 will give you 16. If I subtract 1 from it, I'm going to get 15. Now for 7, that's 1 less than 8. 8 is 2 to the 3rd, which is 8. And then minus 1 will give you 7. 3 is 1 less than 4. And 4 will be 2 to the 2nd if you write as a power of 2. And then subtract 1. And then you can see that 1 is 1 less than 2. 2 to the 1st, and then minus 1 will give you these numbers here. So that formula is this. 2 to some power of n minus 1. So here the total grains would be 2 to the n minus 1. So up to square 20, it's going to be 2 to the 20th minus 1. Here, your n is going to be 20. Now, on the calculator, you can do 2, and then the hat key for your exponent, and then 20 minus, well, you have to use your right arrow key to get out of the exponential part, okay? And then minus 1. So it'll be 1,048,575. Okay. So again, 2 and then the hat key and then 20. Right arrow to get out of the exponential minus 1. So in this case here, the total number of grains after the grains of wheat have been placed on square 20 will be 1,048,575. And then finally, what is the total weight of all the grains of wheat on the board after the grains of wheat have been placed on square 20? Okay, we're told that we're to assume that each grain of wheat weighs 1/7,000 of a pound. So, the total weight will be, we got 1,048,575 grains. We're going to multiply that by 1/7,000 because that's 1 grain of wheat weighing 1/7,000 of a pound. So that means I have to do 1,048,575, divide that by 7,000. And we're going to round to the nearest tenth or to 1 decimal place. We're going to say that's approximately 149.8 pounds. So in this case here, the total weight will have to be 149.8 pounds after the grains of wheat have been placed on square 20. Okay. All right, next example. Let's say we have this. A leprechaun places a magic penny under a girl's pillow. The next night, there are 2 magic pennies under her pillow. Each night, the number of magic pennies doubles. How much money will the girl have after 19 nights? Okay, what I'm going to do here is create a table. So it'll be for the day, and then for the number of pennies, and the amount. So on day 0, there's only going to be 1 penny. Day 1, there'll be 2 pennies. Day 2, this doubles to 4. Day 3 doubles to 8. And on day 4, doubles to 16, and so on. So pretty much you can see there's a pattern here. This is going by a power of 2. Because I know 16 is 2 to the 4th, 8 is 2 to the 3rd, and 4 is 2 to the 2nd, 2 is 2 to the 1, and the number 1 is 2 to the 0 power. Okay, now, the value of a penny is 1 cent, which is, of course, 0.01. And that's going to be multiplied by the number of pennies she has. So it'll be 0.01 times 2 to the 0, and then 0.02 times 2 to the 1, and then day 2 be 0.2 times 2 squared, and pretty much I'll fill in the rest. This should be 0.1. Not sure where I got 0.2 from. That should be 0.01 times, and this last one, 2 to the 4th, because the amount of the penny is 1 cent, 0.01. Okay, now, let's see, for day 19, the value of the pennies are going to be worth this, 0.01 times 2 raised to the 19th. Okay? Based on this pattern right here. So if I take 0.01 on the calculator, multiply that by 2 raised to the 19th, that will be the amount she will have. So on the 19th day, day 19, the girl will have $5,242.88. Okay, so that's how you do that particular problem on the impact of doublings. Okay. Here's another example. Suppose a single bacterium is placed in a bottle at 11 o'clock a.m. It grows and at 11:01 divides into 2 bacteria. These 2 bacteria each grow and at 11:02 divides into 4 bacteria, which grows and at 11:03 divides into 8 bacteria, and so on. Now suppose the bacteria continue to double every minute and the bottle is full at 12 o'clock. How many bacteria are in the bottle at 11:43? And what fraction of the bottle is full at that time? Okay? The way I see this, the bacteria population is doubling, so it's going to be like 2 raised to the n power, where n is the number of minutes. Okay? Now, we want to find out how many bacteria are in the bottle at 11:43. If it's placed in the bottle at 11 a.m., if we subtract 11:43 minus 11 o'clock, that means we want to find out how much bacteria is in that bottle after 43 minutes. Okay, so that means that there will be 2 to the n, and n is going to be 43, 2 to the 43rd bacteria in the bottle at 11:43. They want us to give the answer in exponential notation, so I'm not going to evaluate what 2 to the 43rd power is. They just want 2 to the 43rd in exponential notation. Okay, now we want to find out the bottle will be blank full at that time. So here we want to find out what fraction of the bottle is full at that time. Now, let's think about this. At 12 o'clock, the bottle will be full. And here, now keep in mind, the n is going to be the number of minutes, so if it's placed in the bottle at 11 o'clock and it's full at 12 o'clock, the time lapse on that was 60 minutes, okay? So at 12 o'clock, where n is going to be 60 minutes, there will be 2 raised to the 60th bacteria in the bottle. So, if I want to find out what that ratio is, that's going to be the number of bacteria in the bottle at 11:43, which is 2 to the 43rd, divided by the number of bacteria in the bottle after an hour when the bottle was full at that time would be 2 to the 60th. Okay? Now, for exponents, when we divide powers of the same base, we keep the base, but we subtract our exponents here. Okay? So in this case here, I'm going to bring over the 2, which is my common base, and then I'm going to subtract 43 minus 60. So it'd be 2 to the 43 minus 60, which is negative 17. So it'd be 2 to the negative 17th. Now, with negative exponents, we always write it as 1 over that base with the positive exponent, okay? Because there is a rule that says if you have a to the power of negative m, it's going to be 1 over the base of a, and your exponent will be positive. So 2 to the negative 17th would be 1 over 2 to the 17th power. Now they want this as a simplified fraction, so we need to evaluate what 2 to the 17th power will be. That's going to be 131,072. So the bottle will be that fraction of 1 over 131,072 full at that time. Okay. Okay, now we can wrap up this video with some key facts about exponential growth. Here, exponential growth leads to repeated doublings. Here, with each doubling, the amount of increase is approximately equal to the sum of all preceding doublings. Okay? And also, exponential growth cannot continue indefinitely. After only a relatively small number of doublings, exponentially growing quantities reach impossible proportions. So in other words, exponential growth is not going to go on and on and on and on forever, okay? Because it's going to reach its limit somewhere, okay? All right, so that's all I have on this particular video, and that's going to wrap up that video on growth, dealing with linear growth and exponential growth.